So I have two challenges. Number one, that this is the first session after lunch, so I don't want any of you to fall asleep. Okay. The second challenge is that there are probably popular topics elsewhere, so thank you for being in this room. It's going to be nicely close-knit family of friends. My name is Haresh Malkani. I think you may have heard me before. I'm the Chief Technology Officer at CESMII. This session is going to be focused on the work that we are about to do in the next couple of years around scaling and deploying smart manufacturing solutions for energy-focused industries and clean energy industries. And this is sort of the foundation of a request for proposals that's going to go out fairly soon. And so this is the level of information that we can share at this point in time, but I would say that the details will be in the upcoming RFP. And what I'm going to do is to show you some examples of what we have done in the conventional industries that are energy intensive. So before we go anywhere, just read the antitrust statement. All participants in this meeting, we need to be mindful of the constraints of the antitrust laws. There shall be no discussion of agreements or concerted actions that may restrain competition. This prohibition includes the exchange of information concerning individual prices or any other competitive aspect of an individual company's operation. Each participant is obligated to speak up immediately for the purpose of preventing any discussion falling outside these bounds. So I'm going to repeat this slide because it's important to set context for the rest of the discussion. But when we said we're going from CESMII 1.0 to 2.0, we said we're going to be focusing on scaling and deploying. So I'm just repeating what that means here. And the one that is important here for this particular conversation is number one, of course, right? Perhaps number two, this is less of a supply chain. That's actually the next session. It could include the functional scaling. It could include proliferating the solution across the nation. And of course, always the ecosystem scaling. So a lot of points that apply to this particular sector. So within the DOE funded contract that we have for the next 5 years, these are the key initiatives that we've got. The second and third are directly related to the request for proposals that's going to go out, and we're going to talk about the second one here right now, and then this one in the next session. But part of it falls into some of the other capabilities. So I'm not specifically talking about this item in this session. And then Conrad is already talking in the other side about the workforce development initiatives that we have. So just to set the expectations about what we're going to talk about. So we sent out a notice of intent a couple of months ago. Typically, when we do RFPs, we first send out the notice of intent so you can actually start building teams and be able to respond to the RFP. So in that notice of intent, we had highlighted these two flavors of the project, and we're going to talk about this one first. And this deals with scaling of smart manufacturing solutions in these industries, and the examples that we've given are some of the energy intensive industries like cement, steel, chemical, and paper, but also we want to explore smart manufacturing for clean energy industries like batteries and solar in the same way. There's not a whole lot of information I can share in terms of the details of the RFP because by law, I'm not allowed to do that, and I won't do that. But roughly speaking, we're talking about $1 million of federal money for each of the projects. There would be 2 projects. Each would be roughly about $1 million, matched by another $1 million from the members. So it's a 50-50 partnership. The the typical length of the project in this case, because these are fairly heavy, industrial implementations, we are thinking maybe about no more than 2 years, but no less than 18 months is my guess as to how much it will take. The makeup of the team, we don't have any restrictions on that. We always encourage that you have a manufacturer who's part of the team in a fairly substantial way, either leading the team or be a significant role player in that effort. That always helps in the selection process. It can be led by the manufacturer, or the manufacturer has to have a very significant role in the team. Yeah. Okay, so let me just go back 1 second. So before we go to the interactive question here, unfortunately, this is just the level of information I can share today. But through Q&A, I can clarify other things as they come to your mind. So if there are any questions at this point, I'm happy to take them. And if I can't answer them, then Sudarshan will answer them. He promised me. So yeah. But what I'll do next is to just show you some examples of what we have done, because the idea behind this RFP is that you take a look at what we've done and then see what can be taken forward as scale and deploy, what can be reused in other industries, or what can be expanded in terms of functionalities. So okay, so let's do this first. If you go to the Slido, you should see this section. Select the session that says Smart Manufacturing for Energy. And then if you can, I think this should be updating on its own, but okay. And this should be free format, I think. Did everybody answer cement? There you go. That's good. That's a new one, poultry. Yeah. Site and aluminum, close to my heart. Okay, that's good. Good to know. Good to know. And this will be open, so if you think of something later on, you can just add to the thing. So thank you for that. So what I'm going to do is I'm just going to go through some examples. I've got maybe 10 examples. I won't spend a lot of detailed time on it, but at least give you a flavor for what these projects were, what impact they had in the respective industries. And then hopefully that will give you some idea of how we've been able to use smart manufacturing in these use cases. So this is a use case in the you could call it oil and gas, but we had project partners that were from Texas A&M, and then back then it was called Praxair, it's now Linde. They were the partners. We had Emerson as another partner, and other folks that were the technology providers. that came together. The idea here was that the air separation unit is a fairly common piece of equipment in that industry, and that a small percentage change in how you operate that results in some huge impact on energy consumption. And so what they did is they came up with a strategy where they were using digital twins that were fairly high fidelity, and then from there they extracted surrogate modeling that could actually execute in real time, right? So when you talk about real time operations, you can't wait for hours for a model to provide the results. So they created a bunch of dynamic models, and then out of the steady state models, they had real time applications that were created, and then worked in conjunction with real-time access to data from our partners in Emerson. They had a data pipeline that fed through, and then to compare what the real-time process is telling you versus what they were predicting, and that was tied together for them. So they demonstrated that this was something that was feasible, and then they took it to Praxair. I think they tested the applications. They were fairly confident that can be used. We haven't got to the point where we can actually install that on an industrial facility and run it as production. So this is why this is important in this conversation. When you talk about scale and deploy, then you want to actually take it forward and do that. Yeah, that's a question. Yeah. I'm going to pass the microphone around so that we get recorded, if you don't mind, and I'll keep it there.
So basically, if I understand correctly, you compared the real-time data of energy performance with what you modeled with the digital twin, what it should be, and that delta you then used to define improvements to get closer to the model,
Correct.
right? That's
Correct.
what it is? Okay.
And the model, of course, helps, do the what-if scenarios, right? So if you're going to change the operating conditions, it'll say that if you did this to the operating conditions, here's the result in quality and performance.
Yeah. Okay.
Yeah.
Okay, great. Yeah.
So one example, this was in oil and gas, chemical, depending on how you look at it. And what I've done on each of these slides will be made available to you after the event. You have to sign up for, there's a form for signing up, and then it'll send you the link to these. And the reason I mentioned that is that in all cases, you'll have the contact people, right? So if you, for example, if you're thinking of doing a scale and deploy project and you want to do it in this area, you can contact them to join hands and take it forward. Okay. This is an example in the food industry, and I think you've heard enough about ThinkIQ from their platform capability standpoint. But here's an example of how they actually used the state-of-the-art platform with General Mills, and then they created these energy analytics and consumption applications on top of it. And they had real-time connectivity to their assets. And as they looked at where energy was being consumed, from little devices like pumps and motors to large equipment like mixers and other processing equipment in the flow path. And the other thing they did is that they actually had a way to classify the total energy by product. So this is YP stands for Yoplait, by the way. And so they were able to go into this and break down which particular product was more quote unquote energy intensive. So they could break it down and go after that particular flow path and the equipment, and then make the modifications there. A lot of other things got highlighted as a result of this because before they went in with this system, they had zero visibility to what was happening. The only visibility they had was at a plant level, right? Which doesn't necessarily help nail things down. So this is the food industry. They also had another example. Somebody mentioned poultry in the previous thing. ThinkIQ actually did another project with the I can mention the name Tyson. So they're a chicken processing facility, and they've done some work. Sorry, there was a question.
For this example and the previous example, can you elaborate on what the underlying challenge was? Was General Mills having issue? I got to imagine they were collecting some of this data.
Yeah.
Was it dispersed data sources that the platform helped pull it together, or was there another underlying challenge that the project created?
No.
For this one and the last one?
Yeah, it was what you just said. So they had data coming in, but it wasn't contextualized in a fashion that would allow them to take any actions, right? So the platform kind of provided that. So the data modeling piece that you saw in the other sessions was critical for them to understand. And the breakdown that I was showing here, this particular breakdown would not have been possible without that particular context. So that's for this one. In the previous one, this was a case of where just understanding the behavior of the air separation unit wasn't up to the maturity level that could be applied to like real-time processing, right? So they had digital twins. I mean, that's a pretty old process. There's a lot of digital twins there for that. But to actually take those and make it applicable for real-time applications was the challenge. So that's where they went into this type of approach. And then they created the fault detection, optimization, predictive control. These were the modules that went in for control purposes. Yeah. One second, just microphone. Yeah.
Question: do you choose the industries, or are we given the opportunity to bring an industry?
Yeah. So when you respond to a request for proposal, you can identify the industry.
Okay.
Right.
Okay.
I mean, we list some examples because just to give you some guidance, but you can propose any relevant industry.
I just wanted to add to the next example that you had in there. One of the challenges we had also was that in many instances, you cannot collect data because of the expensive, instrumentation that you have to put into the different places. So that was one of the targets here. It wasn't really just, get to the energy losses and reduce it, but it was also do it very inexpensively without spending a lot of money in just instrumenting, all your equipment. So that was the other challenge that we had in this case.
Yeah. Okay. This is another industry. So this was aerospace and pharma, but it deals with traditional, subtractive manufacturing, which is basically machining, and additive manufacturing. So this facility at Yukon, and the partners were Johnson & Johnson and Raytheon and CCAT. And here they took a approach that was at a systems level. And they said, here's a flow path of equipment that you have, which has both additive manufacturing, subtractive manufacturing. And then as you route your products through it, how do you then come up with a systems level model that says, in order for me to optimize energy usage on this particular product flow path, how do I do that? So they took a systems approach here. But as part of that, they did develop things like tool wear estimation models. So as you're doing the machining, now it's able to predict when the tool is going to go out of commission. And then based on the data that they have from these partners, they also created a model that would predict the probability of generating scrap, which is probability of generating scrap doesn't sound good, but quantifying how much of quality issue you might have. And the third one was to then optimize and plan how you would actually utilize the assets. So this is a slightly different flavor. And again, like I said, I mean, George Bolus is the key person here at Yukon who ran this. So, people have sort of come back to me and said, well, the machining models have existed for years, right? So if you're from that domain, you know that people have done research for a long time. But what's different now is that the speed at which the data is available to you as you're machining has changed significantly, and the speed of processing that data has changed significantly. So that brings up this advantage of using machine learning and other techniques to come up with more data-driven approaches, and that's one of the things that they did. So steel is a big energy user, as you know, and in this case, Arcelor Metal were now Cleveland-Cliffs. They made a proposal with their partners at RPI and Purdue and Missouri University of Science and Technology. The main theme for this project was to be able to predict the quality at the end of the hot rolling process based on what you're doing in the continuous casting process. So if you're familiar with how steel is made, the very first step is this one, where molten metal comes in through these segments and it cools down and it creates a slab at the end of the process here. But it's very critical to understand where the solidification occurs. And that's a function of many, many operating parameters, obviously. But there's no in situ measurement that tells you where that solidification occurs. So Missouri Science and Technology went in and created a three-dimensional sensor that could be mounted underneath one of these segments. And they also came up with a strain sensor that could operate in that environment. And between the displacement and the strain, you could actually predict where exactly the solidification is occurring, right? So they tested that at their site, and they were happy with the results. So that technology exists, and there's a whole bunch of specifications on what the sensor should look like, and there's a processing algorithm that's associated with it, and any validation results that you might want to add. So if you just take some of these things and say that, hey, for scale and deploy, I'm willing to partner with somebody and actually take it to multiple casters in the country, that would be a fantastic project, right? So, it's not deploy in production. It was our job is to develop and demonstrate. So it's demonstrated at an industrial facility, but then now we are moving into this scale and deploy thing. So, related to that project or part of that same project, Purdue worked on a continuous caster digital twin. And the idea here was to get a digital twin that was based on physics, but then matched with real-time data that's coming from the floor. They didn't quite finish that second part because of some challenges we had at the manufacturing facility. But nevertheless, this continuous casting digital twin is now actually available, and that was given to Cleveland Cliffs for their maintenance personnel to be able to use that. So, and then as part of that, we also asked them to create the information model that would become a profile that goes into our platform marketplace. This particular twin isn't something that is available through the platform because of the intensity of the computations, but Purdue as a partner is making that available to CESMII members, through us. And the last piece on this one is the clogging predictor. This is for those of you who have exposure to this. When you have molten metal operations, as the metal is flowing through into the cast, and if something happens to the nozzles and the orifices that send the metal down to the chambers, if that gets clogged, it's a huge deal in terms of it just freezes everything up, and the cleanup could cost you anywhere from half a day to 2 days. Production stops. There's a huge deal in terms of the downtime. So being able to predict this through machine learning approaches was one of the things that this team did. So they have a machine learning based clogging detection algorithm, which is using the signals, real-time signals from the casting operations, and then able to predict based on that it's pretty close to getting clogged. It flags the operator, and the operator can either change the settings or go do something to fix it. So those are steel examples. Here's the cement example. So University of Louisville Any questions so far on the ones that I presented? Um, so the problem here was that the kiln is like, I think it represents about 60 to 65% of the energy that is used in cement production. So it's a huge deal if you can change that, and if you can cut down by 10%, that's a huge deal. Every cement manufacturer has this. What they did is they created almost an industrial size kiln, and then they instrumented it. They developed both data-driven and physics-based models for it, and then tied it back into an advanced control strategy so that you could go from sensing to machine learning models to predictive, physics-based models to an advanced control system. They took that entire package to Argos, which was the industrial partner, and then they ran it at their facility in what's called a shadow mode, meaning that this system was running in the background, providing the advice to the operators as to, I think this is what should be done to optimize. In the end, the operators still had to say that, yes, I accept this or not, which is a good strategy. But they were very happy with it. So what they've decided now as an extension is that instead of just the kiln, they've now gone upstream and included the pre-calcination process to get even additional benefits in energy conservation. So again, these are things that are available for other members to utilize, and again, this is actually one of my favorite stories to tell. So somebody was asking me about, oh, David, you were asking me the question about McGinley. So so that's cement. This is aerospace and composites. So Virginia Tech, Penn State, and Honeywell, they partnered in creating the real-time in-process data monitoring for their operations. And again, this was machine learning-based algorithms. They also had the process was this chemical vapor infiltration, and that's a pretty advanced process. You don't have a lot of in situ measurements, and to optimize the thermal operations and the furnaces to get to the quality is a challenge. So they were able to create a monitoring system. They were able to get the data architecture necessary to capture that data and then create the machine learning models from it. So another industry example. This is on CNC grinding. One doesn't think that it's a high intensity energy industry, but these are, I think the size of this, Miguel, remind me, I think it's like maybe 2 meters in diameter or something like that. It's really huge. And to go through the grinding process for some of these large components is a industry sector that's of interest. And so here again, they created a hybrid model. So they had physics-based approaches as well as data-driven approaches, combined them into a sort of a dynamic control strategy, and then have the predictive models available for us, physics-based models available for us, and then obviously create a SM profile for the grinding process, which is made available for other members. Yeah.
You're also looking at the other end of this as near net chip manufacturing for large products like this. So the machining of that is limited there because you're creating near net shape. What are the lessons learned from that can be used for near net shape? So you should talk to Nick Nelena to see whether he needs any of these that it can work for him, and there's a potential for. I think he's working on something to see what are the things that he can.
Yeah, I mean, there's potential there.
Yeah,
there's potential there.
Do you know Nick and Elena?
No, I don't.
So I'll send a connection to you.
Yeah. But it's an interesting point because one of the things that can be done at the next level, right? So you're actually looking at the grinding operation now, right? But how does that impact design, right? So if you're optimizing this for energy, it might say that maybe starting with a different geometry is a better option,
Yeah.
right? And then you can link up there. Yeah, good point. This is again Honeywell as our partner with Virginia Tech. This is another phase of the project where they looked at how actually one of the unique ones here was that when you have discrete parts that are being processed in thermal operations, it's important to know how these parts are placed in the furnace and what is the optimal location for that. So if you're in the aerospace industry, this is a common challenge. And so they came up with some algorithms to optimize the location of these parts as they're being processed so that the quality remains the same, but you end up using less energy in the thermal processes. So there's a part loading optimization piece of it, load placement. And then even for the thermal operations, what are the operating set points that are optimal for creating the quality that's required. So another example there. Pulp and paper. Auburn and Rainier. I actually talked about this example elsewhere as well. But they in the washer process. So this is the pulp washing step. If you have a sense of how much air is entrained in that pulp, you can actually get a better sense of how to operate the equipment to optimize. But there's no in situ measurement available for that. So what they did is they created machine learning models that would look at everything around the washer that can be measured, all the operating points, all the information that is coming from other sensors. And then they created a machine learning based algorithm that would provide this soft sensing of the quantity that was of interest there. So this brown stock washing process step is very common in pulp and paper. They in my other presentation, I said they reduce, like, defoamer is something that they use to balance the consistency of the pulp. But the defoaming agent is not necessarily the best thing to use, right, from a sustainability standpoint. So this cut down, Miguel, remind me, I think on an average, it was like 36%, but they went as high as like 60 or 70% reduction in usage of it. So again, from a sustainability standpoint, we are trying to see how these smart technologies can make an impact. So again, here the data-driven models, the algorithms, and the soft sensor for moisture content is the key thing here. They worked with Rainier in the beginning, and then we kind of extended their project to try this out. So they were, to some extent, they've done a little bit of scale and deploy with two other companies. So International Paper and Georgia Pacific in particular. So they're actually in the middle of, they finished the project. They're wrapping the project up now. This is for agriculture. So the hop drying process. This particular team worked with 5 different hop dryers in the Pacific Northwest. Hop drying is a fairly old, uninstrumented, unsophisticated process in terms of control. Typically, the set points are just determined through historical knowledge, and they're not necessarily optimal. So they instrumented some of the furnaces, and then created predictive algorithms that would tell them what is the optimal time that you need to set the furnaces for, and at what temperature, without without wasting energy on it. So, and I think it's only maybe a 20%. I can go back and check, but I think it was about 20% difference in energy usage with and without the algorithms. I have maybe a couple of them, and then we can have a discussion. This is again with the steel industry. This was more of a method to classify strip breaks, but then do it in a fashion where it becomes predictable. So you could actually monitor some of the operating parameters in real time and then run the algorithm and actually predict if this is going to cause a strip break. Strip breaks are again a big downtime for any rolling operation. So this was tried out at Arcelor, and Falconry was the technology provider there. So again, it's for steel cold rolling, but I came from the aluminum industry before I started with CESMII, so this is very relevant to any metal rolling operations. And the last example, and this is actually the only example within CESMII that touches upon clean energy production. So, we stand guilty here that we haven't done a lot in that. But in here, this was around, it's more to do with inspection, but automating the inspection process through advanced technology like augmented reality. And the amount of difference it makes to cut down on inspection time and rework and all that stuff. So, and this was for windmill blades. And the GE Renewable Energy was the industrial partner. Spiral Technologies was the technology provider here. So on our website, oops, okay, go back a little. So these are just a few examples of the project. They're all sort of more or less related to energy. But on our website, you'll find more detailed descriptions of all of the projects we've done. And feel free to take a look at it and see if you're interested in responding to our RFP. It might be a good idea to do that. And there's a lot more detail on each of these projects available there. So, and outside on the front desk, there should be brochures that have the 2-page documentation as an overview for each of these projects if you're interested in. Okay, so next question here. Has CESMII provided relevant examples of industry use cases on energy to invite good proposals on the RFP? So please take a few minutes and respond to this if you can. Be shy, you can say no. You can handle it. It could be. Okay, well, that's good to see. But yeah, I mean, if
can I say something really quick
Sure.
while you're doing that? Haresh mentioned in the website, you're going to see a lot more information on these projects. One thing that is missing here you see in the website is the matrix. How much energy did we actually saved by each of these projects? So you can have an idea, okay? So you see the technology and everything. Yes, we target that, but how much what we're talking about? So you'll see that in the website in every description.
Thank you, Miguel. Okay. So time for Q&A and anything that I can share that would be beneficial for you, what you heard or. Yeah.
Thanks. I think there's a lot of really impressive applications. It's cool kind of seeing it all come together with the lens of smart manufacturing. My question is about, I think, retention, because that's probably the big thing, right? It's to come in and clearly there's something because they're able to do this across the board on a lot of different projects. But can you say anything about retention? Like how many of these companies said that one project worked great, it was easy, let me do it again, and then they've taken off using this without the need for funding? Have you, it's probably also hard to capture, you may not always know, but can you say anything about that? Have people picked it up and ran with it, or is it they're still learning and growing?
Yeah, so I'll answer it in two different ways. One is that many of, and I actually pointed out some of them that had what I call extension funding from us. So when they proved that a certain technology works, we were impressed enough to say that, yeah, if you want to extend this to other manufacturers, then we can, support doing that. So that pulp and paper example is one. They proved it in one case, and we said, okay, this is something that, has a great return on investment. We are willing to fund it even more. And then the industrial partner came in and actually put in a lot more effort in trying those out, right? So there are a few examples like that. Food industry is another one that we have an example. But we are right at that cusp now, right? So we've just finished our first tenure. We are now saying we are ready to scale and deploy, right? But that's where I think industry partners need to come in and say that, yes, I'm raising my hand to take this forward. I know enough about the technology. I'm satisfied with how it was demonstrated, and now I can take it forward, right? Now, in many cases, right, they still need an incentive. So maybe not 50-50 funding, right? We might even say, here's some seed money, maybe 20% of the effort, but now put in 80% and actually implement it. So there might be some models around those kinds of things, which we haven't, I mean, we are exploring it, but we don't have a how to execute it just yet. We're just on that cusp right now.
I just wanted to mention that we do have a couple of examples where they have developed the solution, we tested it, and for example, General Mills with the inferential energy savings, I think it was the second project that you mentioned, Haresh, they're already going ahead and implementing that in their different factories. We don't even know how many they have implemented because we know they're already doing it. In other cases, the problem is that their budget cycle. They said, yeah, we want to do it, but we have to wait a year until we get the funding internally. So it's a matter of scheduling, putting it in the annual budget and then continuing with it. So a lot of good examples like that, but they're just waiting for the funding.
Yeah, it's always a great pleasure to see your amazing achievements. So I know CESMII has focused on supply chain, sustainability, workforce development, energy efficiency. Have you prioritized these features, and in which one you had the highest impact, and how the others
You were not supposed to ask difficult questions. I
Sorry.
No, well, it's a balancing act, right? I mean, so what we've done over the last 6 years, for example, is that we said, okay, in order to go after some of the larger industries, energy intensive industries, that usually takes a longer time frame, right, for the project to actually execute. So we did that early, knowing that it's going to take a long time, right? So all of our first RFP projects were longer term, they were, more complex and so on and so forth. They happen to be focused a lot more on energy than the later projects. The later projects, we knew that as a 5 to 6 year contract with the DOE, we had to start the projects and complete them in time. And then we said, okay, how do we invite smaller manufacturers to be in the ecosystem? So that's when the supply chain, the SMM focus came in. And now we said, okay, we're going to execute shorter projects so that we can impact more small manufacturers to come and be part of the ecosystem. Workforce development kind of goes along, and it has its ups and downs in terms of how much investment we are making in it. Again, like any other thing, that's also an ecosystem type of an approach where we have academic partners, we have industrial partners who help us with creating the content, delivering the content. So again, as we partner with organizations like MEPs and other regional entities, then the internal effort becomes different. The external effort becomes different, right? So we try to, so there's no single model for it. It's just, I think as we go along, we try to prioritize them. Right, guys. Good question. Okay. Well, I think if there are no other questions,